Thank you. So we are here, we come together with shared purpose today to rethink how cities move, how public transport can be redesigned, and how can we transition from a mass system to flexible, individualized services based on efficiency, equity, and strategic design. So this is the team. I'm professor at the UPC together with Professor Franza Robusti, and these are the team. So the vast majority of contributions have been developed together, okay, with the team of Professor Robusti. We co-authored the vast majority of the papers developed or dedicated to this topic. So this is the content of my presentation. First of all, I will you introduce to the urban challengers. Later on, we are going to review the economics or the properties of a collective transportation, or what we call, okay, mass transit services in comparison to individual transport. Later on, I'm fill you in on the system modeling, so the modeling approaches in order to calculate expected values of the access time, waiting time, and in-vehicle travel time in this kind of service. In the fourth topic will be devoted to the introduction of flexibility. So how can we reduce, okay, the constraints of fixed layouts and given in time headways to a more demand-oriented layout or scheme in which flexibility is introduced in the timetables and in the layout. And finally, we are going to compare the performance and the operational cost of the different services and to draw conclusions and insights. Okay, let's begin with the first topic to be addressed. So you know that cities today face unprecedented challenges, growing populations, environmental pressures, an urgent need for more equitable access to mobility. So we all know that more than 25% of the population live in urban agglomerations. So in that context, private vehicles or individual modes, okay, may improve all these terms, okay, related to energy consumption and emissions, but they will contribute to the congestion episodes, to the accident rates, and they present high travel times in these congestion episodes. So in that context, public transportation or mass transit can be more than a system of lines and stops or vehicles. It can be a tool to mitigate congestion and an engine of environmental transformation. So we have to design these systems efficiently, and this is the aim of this session. So before going on, let me introduce you to this timeline, okay, the introduction of the different innovations in public transport. So before the 19th century, okay, all the services were animal powered, so the powertrain was based on animals. It was individual transportation, and it's in 1830 when we introduced the common cabin. So different people share their trips in order to reach their destinations within the same transportation mean. During the next 30 years, we introduced the ground rail services. So we provide the steam services, or we have widened the paths, and we introduced larger cabins. In 1863, the first underground metro. So we identify, okay, the potentialities of the right of way, the separation of modes in order to increase the commercial speed. And in the last years of this 19th century, okay, it was the advent of the first car powered by internal combustion engine. Everything changed, okay, from this point. This was a tipping point. And from that point on, okay, we have this development or this explosion of passenger cars and infrastructure adaptation to the needs of private cars, at the same time that we introduce bus services, electricity in public transportation, and the first autonomous trains until 1960. But there was another tipping point in 1980 when collectively, okay, we took awareness of the congestion and the externalities caused by the mobility system. So We were aware of the air quality, the climate change awareness, so that we change our mindset and we foster the introduction of collective transportation, efficient collective transportation modes. So we live in this new paradigm, and our mobility solutions, present a trade-off between this social and environmental awareness, in terms of efficiency and emissions, and on the other side, the convenience for the final user. So we have to provide or deploy appealing services, competitive service, but at the same time, we have to do that respecting, or deploying zero emission systems, and other systems that will fulfill some principles in terms of equity, in terms of safety, and in terms of sustainability. So if we focus on the economics of mass and individual transportation, we have to highlight this main difference between the average cost of private vehicles, that is individual transportation in green, and the average cost of metro, trams, and buses, so mass transit. As the demand increases, collective transportation presents economies of scale, and the average cost declines. This is not the tendency of the private vehicles that presents increasing average cost when the demand is increased due to the effect of congestion. And we have to highlight, this phenomenon in terms of the optimal equilibrium in a mass transit. So you know that the optimal point of equilibrium in one system is when the curve of the marginal income intersects, the cost of the the curve of the marginal cost. So in that case, the optimal equilibrium is R star, that is higher than the real point of equilibrium in these systems in R prime, that is when this curve, the income, the marginal income, intersects with the average cost of the system. So if we take a look at this picture, we can realize that we should increase, the ridership of collective transportation. And if we don't do that, we have to compensate the operator with some subsidies because the average cost doesn't cover, the needs, in order to run the system by the operator. This is the situation, for instance, in Barcelona. If you take a look on the left picture, the picture on the left, you see that for bus and metro, they capture the vast majority of trips in the Barcelona municipality, but in terms of incomes, they are in the second position. The first position is the taxi. Why? Because taxi has its own pricing scheme in order to cover the full cost incurred by the operator, even if the modal share of taxi is significantly lower than the bus and metro. If we take a look to the picture on the right, we can compare the incomes coming from the fare system to the operational costs. Before pandemic, the incomes represent just the 40% of the operating cost of the running cost of the system. After pandemic, you can see this problematic point in which revenues from their fare only represent 1/4 of the cost experienced by the operators. So we have to be aware of this tendency or this fact in order to operate these systems. So let's focus on the how can we introduce models, or how can we develop models in order to identify this trade-off, this proper balance between the performance provided to the potential users with the operational costs incurred by the agency. It's what we call a multi-objective problem. Why? Because there are some stakeholders, with one objective, with one goal, and there is another stakeholder, the user, with an opposite goal. So we have to define, this term, of balanced term in order to identify the optimal equilibrium point of this trade-off. Okay, usually there is the administration, the local authority, who is responsible to define, okay, the proper headway, the proper spatial coverage in order, okay, to deploy the service. So our models that we are willing to develop should address this fact. So we have to deploy models that will be able, okay, to capture the performance of the system and the operational cost incurred by the transit agency. So we would like to minimize the user cost or the cost experienced by users in terms of this summation of access time, waiting time, in-vehicle travel time, and transfer time. Okay, so the generalized cost of user will depend on the summation of this fourth component. And at the same time, we'd like to minimize the agency cost in terms of the infrastructure costs and the operational costs based on the distance run by the whole fleet and the number of vehicles and drivers required. So we can formulate an objective function that will be the summation of the agency cost plus the user cost times the demand, lambda, and beta, the value of time. Okay, of course, we can introduce more costs incurred by other stakeholders. So, for instance, it's quite easy to introduce as well the external cost, or for instance, the emission cost here as a term that will depend on the decision variables of the system. So, for our easiest implementation or problem, that is one corridor, the planning or the process of planning this kind of services is equivalent to optimizing this function, okay? With regard to two decision variables, and these decision variables are the time headway and the stop spacing. So the time headway is the inverse of the frequency, okay? So more time headway or higher time headway implies, okay, a less frequent service, so people will wait for a larger amount of time. And stop spacing, it will be the separation between two consecutive stops. So if we increase the stop spacing, we are going to worsen the accessibility of the corridor. So our idea is to identify the combination of S and H, the values of stop spacing and time headway, that would minimize the summation of the agency cost and the user cost, subject to a set of constraints that we are going to see. So let's focus on the easiest problem, okay? One corridor in which we would like to deploy stops evenly spaced at S units of distance, okay? So it can be easily derived that the access time for a user, okay, that is willing to get stop in order to reach a destination would be 1/4 of S. This is the average distance, okay, in the access time. We multiply by 2 because we have to take into account access and egress time. Okay, so at the beginning, from the origin to the stop, and from the last stop to the destination, and we divide by the walking speed in order to translate distance into hours of access. The same can be done for the waiting time component. Okay, it's well known that the waiting time, if the service is regular, is 1/2 of the time headway at which the line, the corridor, is operated. There is a pending term for the user performance, and this term is the in-vehicle travel time. So the time spent on board the bus or the tram or the subway for a user in order to overcome a length L. L would be the trip length of this user, okay? In this route with a constant stop spacing where the origins and destinations are uniformly distributed. Here, we are going to divide the in-vehicle travel time into 3 components. The first component is the component in which, or the unavoidable component. So one taxi, one private vehicle will spend this time, L, the distance of the trip, divided by the cruising speed in order to reach the destination. However, public transportation, mass transit introduces, okay, stops in the middle of the trip. So the blue component here, L divided by S times tau, it's the time spent braking the vehicle or in braking or accelerating the vehicle every time that the vehicle, okay, reaches a stop. So L divided by S is the number of stops that one user will see during the trip, and tau is the time penalty of due to this braking and acceleration process for a single stop in comparison to a bus or a transit vehicle that won't stop over this stop. And finally, there is a third component that is the time spent dually. Okay, so this is the dual time at stops where lambda is the demand, okay, passengers per hour, h is the headway. This fraction is the ratio of the demand that one user will see during the trip, during each trip, and finally, tau prime. It's the unit boarding and alighting time per passenger. So if we sum up these three components, we can calculate the in-vehicle travel time as a function of our decision variables S and H. And finally, it's time right now to do this modeling approach for the cost incurred by the transit agency. In that case, we are going to compute the cost based on the distance traveled by the fleet in 1 hour. This is equivalent to 2 times the length of the route divided by the headway. And M, it's equivalent to the hours worked by drivers or the number of hours of vehicles needed in 1 hour to provide the service. It's equivalent the round-trip travel time divided by the time headway, or what is the same, the distance traveled by the fleet in 1 hour divided by the commercial speed. Okay, so if we merge all these formulations, we will obtain this objective function to be minimized with regard to S, stop spacing, and H, time headway. So in red, you will see the terms that depend on the decision variables. And in black, you would see the parameters, the input parameters introduced into the system. Okay, so this equation or this objective function is expressed in euros per hour and is the summation of the user cost. So this turns into brackets on the right side is the average door-to-door travel time of a single user that is multiplied by vita t, this is the value of time, and lambda, that is the passengers per hour, the hourly demand. And the term into brackets on the left side is the component incurred by the transit agency. So if we take derivatives of this objective function with regard to the decision variables, we may obtain the size, in that case, okay, of the headway and the size of the stop spacing that would minimize the previous objective function. It's what we call an economic order quantity model. So this optimal H determines, okay, the amount, okay, or the value of the time headway that would minimize the previous objective function, and the same for the stop spacing. We could see that the derivative or the formulation derivative for the time headway depends on the other decision variable that is S, and the same for the objective function or the optimal size of the stop spacing that also depends on H. So how can we determine the pair of H and S values that will minimize the objective function by a numerical optimization procedure? So here in the following pictures, we have developed, okay, and we have carried out the optimization by an enumeration procedure. It means we have enumerated the objective function for a large and wide domain of values for H and large wide domain of values for S. And we choose, okay, the pair of H and S points that minimized, okay, the previous concept. So here you have some examples, okay? This is the case when we optimize, okay, the objective function introducing these input parameters. These input parameters correspond to a bus system, okay? So if we optimize the former process or the former objective function, you will obtain that the optimal stop spacing would be 360 meters and the optimal time headway around 6 minutes. So this design for a bus corridor is similar to the real implementation of bus corridors in European cities. Okay, on average, the stop spacing is quite similar. Okay, so take a look at the total cost of the system. Okay, in the optimized solution is around 5,700 euros per hour. The vast majority corresponds to the user cost. The agency cost is only 739 euros per hour. But here you have, okay, some figures that will help city planners in order to take the first decision, or at least to have the first design, okay, of the current line. Okay, what happens if we change the input parameters and we introduce parameters that will resemble what we know as a tramway, okay, whose cruising speed would be 40 kilometers per hour and the operating unit cost would be higher. In that case, take a look. The system tends to increase the stop spacing and the time headway as well. Why? Because the new transportation mode is more expensive in comparison to the bus. So the system tends to rebalance, okay, this trade-off, just increasing the values of the decision variables. Take a look, the occupancy is very low, 36 passengers per vehicle. And finally, if we introduce parameters that will be more related to the subway, we can consider, or we can see here that the stop spacing and the headway become larger, okay, around 550 meters and around 13 minutes of time headway, okay? So the system reacts to the input parameters, increasing the total cost of the system. Take a look, okay, for a subway, probably this occupancy, 55 passengers per vehicle, makes no sense, okay, to deploy a subway just to cover a demand of 1,000 passengers per hour. So every transportation mode has its own domain of demand where this service outperforms the others. Okay, so in terms of capacity, vehicle capacity or system capacity, we have to start deploying a bus, later on a tramway, and for the most crowded corridors, the subways. So our models, as you can see here, also identify, okay, this tendency that we see, okay, in the real world. Okay, so our models are able to capture these tendencies and are dependent on the input parameters that we introduced. So what happens if we would like to address more complex problems? In that case, for instance, a network, not just an isolated corridor. So in that case, we are going to do the same approach, okay? So we are going to generate different families of design concepts, okay? In that case, you will see a radial network or a rectangular shaped network. And for each family of design concepts, we are going to propose an objective function to be optimized. We are going to identify the optimized values, okay, that will minimize the former objective function. And finally, when we have this first approach, the first design, okay, in terms of this simplified network, transit network, later on, in a second process, we are going to translate the optimized solution into a detailed plan. So for us, planning a new transit service is not just to draw, okay, this map of lines. Previously, we have to address, okay, this optimization problem, okay, and to identify the combination of the decision variables, okay, that minimizes the cost. So in the literature, there were several, there was a wide list of contributions, okay, addressing this concept. Probably the most well-known is the Holroyd that proposed a grid model, okay, so based on this mesh of horizontal and vertical lines. Newell in 1979, okay, he proposed this radial or happen spot concept, and recently the Ganzo, okay, proposed in 2010, okay, the hybrid concept. It is in the city center we have a grid network, but in the periphery we allow corridors to branch out into these branches or antennas just to provide the same uh, spatial accessibility in the periphery, but at the expense of reducing, okay, the number of corridors. That is reducing the operational cost in this periphery, and at the same time, for of course, increasing the waiting time of users in the periphery. So you have in the literature folder, okay, that I share with you, okay, in the digital platform, you have at least 4 papers addressing these concepts. So I'm not going to explain all the details, but one of the questions that I would like to highlight or to share with you is the importance of the commercial and the cruising speed. Okay, so let's focus right now in the grid network developed with Holroyd, and you have all the formulas developed in the digital platform. If you calculate the optimal grid network for these input parameters, okay, using these formulas, you will realize or you will obtain the following design. So the stop spacing is around 310 meters. The time headway is 3 minutes. It means that all corridors, okay, the length of the network is 322 kilometers, and the total cost of the system is 453,000 euros. Okay, this has been obtained for a cruising speed of 30 kilometers per hour. Okay, and we have learned that there is this trade-off, okay, by which, okay, if we increase, for instance, the time headway, if we increase the time headway, the waiting time of users increases, so that the waiting time or the performance of users is worsened, but we can reduce the operating cost of the transit agency. So if we take a decision, this decision will benefit one stakeholder, but will make the system worse for the second stakeholder. But if we focus on the cruising speed, we can realize that if we increase the cruising speed in this network, if we do that, we can realize that the total cost of the system is reduced by, in that case, by 80,000 euros per hour, but we are going to improve at the same time the performance of the user, and we are going to reduce the operating cost of the transit agency. So this is the unique policy driver whose or that may affect positively at the same time to both users and transit agency. So right of way and priority measures are a key in order to make the system better for all the users and transit agencies. Let's move to a new approach, okay, for the transit network design. In that case, this is the hybrid scheme proposed by the Ganzo, on which we introduce more decision variables. Remember that for one corridor, we had just 2 variables, time headway and stop spacing. And in that case, okay, for a grid, we introduce the line spacing, so the separation between vertical and horizontal lines. And at the same time, we introduce a fourth decision variable. And this variable is alpha. Alpha is the size, the relative size of the inner network with a grid scheme with regard to the total region of the urban city, okay, of size dy and dx. So if alpha is equal to 0, it means that all the corridor is branched. So we have the happen spot network. And if alpha is equal to 1, it means that we have a completely grid pattern. Okay, so there are only horizontal and vertical corridors, and we don't have this kind of hub and spoke effect. Okay, so you have the details, okay, in the documentation, but this is the approach that we followed for the city of Barcelona 10 years ago, or almost 30 years ago. Okay, so we compared the optimal design, just introducing corridors, maintaining transfer stations or single stations, and we identified that the optimal scheme was what we call semi-alternate. So the spacing between vertical corridors is double of the spacing between horizontal corridors. This is the scheme or the conceptualized network that minimizes the operation cost and the user cost. And we realized that alpha is the optimal value of alpha. It was 0.85. It means that 0.85 is the relative size of the inner city that will be covered with a grid pattern, and only the 15% of the periphery should be covered with corridors that presents this branch effect. So this is the scheme that we proposed, okay, in order to implement into Barcelona. I have to say something. This scheme was constrained. So the City Council of Barcelona was reluctant to spread the whole system everywhere, and they constrained the maximum number of corridors in the first phase to be 12. Okay, that is why the stop spacing is significant in the city center. However, so this was the final result. So we calculated the optimal values, and finally we translate into a master plan, and this was the master plan. It's more or less, okay, the plan or the lines, the layout of the lines that present the highest ridership in Barcelona, okay, the horizontal ones and the vertical ones that cross the city center. So what happened in a second stage? In a second stage, the City Council of Barcelona allowed to introduce more corridors. Okay, so from 12 lines, they relaxed this constraint and they said, okay, let's deploy the number of lines that we need, that we really need in order to provide a good service. And please compare the performance in terms of travel time of this scenario 2 with the scenario 0, and the scenario 0 was the former bus network in Barcelona in operation in 2009. Okay, so before the new approach, the new redesign. If you can take a look to the first rectangle in red, it means that the scenario that we propose outperform the scenario 0, the former situation, and we were able to reduce the average total travel time by 3 minutes on average. But the main achievement came from the agency cost. We were able to reduce 3 minutes of travel time, and at the same time, we reduced by 1/3 the operation cost incurred by the transit agency from more than 110,000 euros per hour to just 85,000 euros per hour. Okay, we have explored these potentialities of these EOQ models. So we have developed other family or patterns, design patterns. So Hugo Badia developed, okay, the same approach for radial networks, cities, for instance, like Madrid, that can be considered to present, okay, or to resemble a radial pattern. We introduce, and right now we are exploring these phenomena. We introduce what will happen if the city doesn't present origins and destinations uniformly distributed over the whole area. So in 2016, Hugo Badia proposed this scheme in which the city center presents a higher demand rate of trips, and in the periphery, we have a lower demand rate. Yang Ouyang in 2014, he proposed, okay, this new approach for different demand distributions. he presented this tailored service in which the grid can be adapted, okay, to the highest demand or to the lowest demand, just allowing this subdivision, okay, or this new line spacing implementation pattern in the city center or in the zones where the demand is more important. Right now, we have been, or we are analyzing, okay, the potentialities of these new designs, just optimizing the layout, so the position of the corridor within the total area of the city. So right now, we are defining this, and we are going to allow that not all corridors will cross the city from the north to the south. Probably there will be corridors whose layout should be redesigned in order to present an L shape. Okay, so for instance, one corridor that in the city center, this vertical corridor will turn to the left or to the right in order to connect two different points of the city. So based on the origin and destination matrix. So I've summarized a little bit the new contributions and state of the art in the utilization of this continuous approximation approach or parsimonious models in order to address this trade-off between user cost and agency cost. But right now, there is one process or one tendency in the real world that has attracted, okay, the attention of different practitioners and even researchers from all over the world. And the idea is, what happens if we introduce flexibility? So we have mass transportation with fixed routes on the left. We have a completely flexible service, the one that taxis are based on. And the question is, okay, is there something, okay, between this rigid design and this total flexible design in order to better adapt to the demands or the requirements of the demand? The answer is yes. It's the system that is called demand responsive transport, okay, a public flexible transport, user oriented with variable layout. So the idea is to remove or relax, okay, these constraints in terms of the rigid layout of the routes in order to adapt based on the origins and the destination of the demand. However, we have to be aware that this system is not for free, okay? Or this tendency is not for free. As we increase the flexibility of the system, we may expect that the operator and unit cost per trip will increase, and at the same time, the user door-to-door travel time will be reduced as well as the occupancy, okay? So the performance is better when we deploy flexible service, but the cost will be significant, okay? And the question is, if we are in a subsidized system and the operator use or the unit cost per trip is larger and larger, the idea is, okay, can we afford, okay, these new systems? Because the reality is this is a very volatile, okay, market segment. There are a lot of companies that run the system or run the service for 1-2 years, and after this period, they go bankrupt, okay? So the idea is to deploy sustainable, financially sustainable service that can be afforded by everyone. So for instance, one of these service, probably the most well-known service of this kind of flexible or DRT services was in Helsinki, Kutsu Plus, and well, with a personal communication with several researchers from Aalto, okay, they share this figure, okay. The average cost per trip was 18 euros, okay, 18 euros per trip, okay. So it's significant, okay. So you have to have revenue streams in order to balance, okay, this operating cost per trip. So in our case, I share with you 3 different approaches, okay, to model or to estimate the performance and the operational cost incurred by in that case, the agencies or the operators of the DRT services. So we call service A as a transit route that may skip some stops if there is no passenger waiting for the service. In that case, our decision variables will be stop spacing and the headway of this line. We call service B a transit route with a variable layout. So in that case, the bus or the vehicle is allowed to move transversely in order to visit the origins or the locations where the origins and the destinations of the user trips are located. Okay. And finally, we call service C as the service or taxi service. Okay. So here the vehicle is not shared by multiple passengers. It's an individual service that provides a tailored mobility provision, okay, in order to move people, carry people from the origin to the destination. Of course, that a taxi can be shared with other people, but these people will present the same origin and the same destination. So here we don't accept, okay, that the taxi will stop over an intermediate point just to drop part of the passengers on board. Okay. So we did the same, or we followed the same approach. We formulate the agency cost, we formulate the user cost, we gather these formulations into an objective function in order to reduce or in order to minimize or obtain the optimal values for the decision variables. Okay, and here we take into account as well the fare box recovery ratio. Remember from the very beginning or the first slides that taxi service has its own pricing scheme, okay, that covers the 100% of the total cost. In the transit system, remember that it needs to be subsidized. So it's important to identify the fare box recovery ratio, FEC, that ranges between 0 to a positive number. If FEC is below 1, it means that the service needs to be subsidized. If FC is higher than 1, it means that the service is profitable. So let's compare, okay, the results from one case study, okay, with these input parameters. So we conceptualize the service as one corridor that needs to be served by vehicles dispatched every 8 units of time in order to cover this length, 10 kilometers of route distance of the corridor length. The width of the corridor is 500 meters, and here you have the rest of input parameters. So we would like to identify the optimal service for this demand threshold, okay, 25 passengers per square kilometer an hour. And we have two options: to use minibuses, where the fare, here we propose this fare, 1.1 euros per trip, and these unit cost parameters and this capacity that resemble the capacity of a minibus. And on the other side, for the taxi system, we propose this new pricing scheme with new parameters or cost parameters that represent the cost that will resemble a private car, okay? So a private car of 5 seats of capacity. So when we optimize the objective function and we analyze which DRT service outperforms the others, we obtain the following results. Okay, when the demand is very, very low, or this demand density between 0 and 25 passengers per square kilometer an hour, service C, that means taxi, is always the best DRT service. However, if we reach this tipping point and we exceed this threshold of 25 euro passengers per square kilometer an hour, service A, so the service that is resembling the fixed layout, okay, it's not DRT with fixed layout, is the one that presents the lower total cost. As you can see here, service B is not identified. So service B has 0 domain of demand in which it's more suitable in comparison to the others. Why? Because it's more expensive. Okay, so the potential travel time reduction, okay, or benefit savings for the users is not balanced with the increment, okay, of the operational cost. So the operational cost becomes larger and more important than the savings in terms of travel time. How can we identify a room, okay, a suitable room for this service B, the service that was visiting all the origins and destinations of all potential points? Just operating the system with private vehicles. So we don't need minibuses or buses with a vehicular capacity of 22 seats or larger. Why? Because the average occupancy of DRT systems is lower than 5. So with just private cars, we can operate a DRT service, the service that we call B, optimally. And if we do that, we can realize that the domain in which service B becomes the recommended service ranges between 0 to 90 passengers per square kilometer an hour, and only service A, so the service that is resembling the fixed layout, is for demands that will exceed this threshold. Okay? Why? Because take a look here. What happens? Take a look to the picture on the left. What happens if we have a new request from a customer of a service of a vehicle that is carrying more than, imagine, 15 passengers on board? If this vehicle has to detour 1 minute or even 2 minutes just to provide service to pick up this new user, it means that we increase the in-vehicle travel time of the total users by 30 minutes. Just to provide an additional service to one user, we increase the in-vehicle travel time by 30 minutes. 15 passengers times 2 minutes of detour. So these services, when they are optimally deployed, these services must be deployed at a very low headways. Okay, so the average occupancy should be low. So it means that we need very low. Sorry, there is an error here. Low headways, not low frequencies. Okay, so if we increase the frequency, if we reduce the frequency, what will happen? The occupancy on board, okay, will become larger, and the vehicle travel time will be strongly affected by the detours of these vehicles will provide. And this fact has been identified when we analyze this sensitivity analysis of the unit total cost of these DRT services with regard to the demand density. Okay, so in service B, in red, we can identify that as we increase the demand density, what will happen? It happens that more passengers mean more delays, more detours that will increase the door-to-door travel time of passengers, and the unit total cost, okay, in terms of user and agency, will increase. So we have two branches of this curve. The branch in which we can reduce the headway and we can identify the optimal headway, but for a targeted demand density, if we exceed this demand density, the headways cannot be reduced. And in that case, we increase or we identify the congested branch in which every new user will contribute with an additional travel time for the rest of the users on board. Okay, so this branch is the one or is similar to the branch that we saw for the private vehicles when we compare the economies between individual transportation and in mass transportation. So DRT systems may present part of the economies of scale that we saw for mass transportation, but when we identify this phenomena, okay, the system tends to be similar to the private vehicle. So before, or as we come, okay, to the end of this session, I want to return to a simple but powerful idea. Public transportation is not just an operational system, it's a strategic choice about the kind of cities that we want to live in. Okay, we have seen that transit planning is ultimately about balance between user benefits and the operating costs incurred by transit agency, between economics and physical capacity, between flexibility and efficiency. We have seen how analytic models based on continuous approximations, okay, simple but yet robust, can guide us in the design of these networks that can be optimized, reliable, and resilient. And we have seen that each mode, each layout, and each decision has its own domain of competitiveness. Perhaps most importantly, we have learned that flexibility, okay, this concept that it's a trending issue about more among researchers and practitioners, while valuable, is not a universal solution. It brings opportunities, but also costs, and it must be deployed where it truly adds value. So mass transit remains the backbone of the sustainable mobility, especially in dense, growing, and urban environments. And thank you for your attention, and I will be more than happy to answer your potential questions. Thank you.